Okay, so let's go ahead and keep going. We're just going to keep working with this problem. It's kind of a touchy-feely introductory lecture to this. We're going to, again, approximate the area underneath the curve. F of x equals x squared plus 3 from x equals 1 to x equals 9. We're going to use the right endpoint method. Okay? So I want you guys now, and hopefully you got somebody sitting next to you, go ahead and give this a shot. Okay? Give this a shot. You're gonna mimic everything except for your rectangles. In fact, I'll help you out. Let's draw this first rectangle here. My first rectangle will be this rectangle right here. All right, give it a shot. Oh,
yeah, that's right.
I have 2 more 5-1 copies. Someone need a copy of 5-1? No. This second rectangle then would look something like this, right? And then here'd be the third rectangle. And then last we get the fourth rectangle. Okay, folks, this is good practice. I want you to keep working through this. I'm going to keep, as each time we go through, I'm going to kind of step up the level of rigor as we go through this just by a little bit. Okay. I want to return to our fence posts that we talked about. Notice that in this problem, are our fence posts different than they were in the last problem?
Yes. Well, no.
I don't think our fence posts are any different, right? I don't think. So we're going to give this thing a name, okay? I'm going to say that what we just did is we partitioned the region, okay? We partitioned the region into, we partitioned it with how many values? We partitioned it with 5 values, okay? So we're going to say here that our partition would be, so what was the first one? Well, let's go abstractly first. We're going to start counting at x0, x1, x2, x3, and x4. Those are the 5 values that show up in our partition. Okay. Folks, this is going to be challenging for this section. In math, you can start counting wherever you like. Counting is just a sorting procedure. Watch. Okay? -3, -2, -1, 0, 1. Right? I just enumerated these 5 items in a sequential way. Okay? Oftentimes we will count for our partitions. We will start enumerating the values in the partitions at 0. And we'll see why as we go along. Okay? Anyway, here are the 5 values in our partition. The 0th value is 1, then 2, then 3, then 5, then 7, then 9. Okay? So this is 0, 1, 2, 3, 4. Those are the 5 values in the partition. Okay? Now, the reason why we count them that way is because that enables us to make the intervals count the way we would expect to count the intervals. So the first interval goes from 1 to 3. The next interval goes from 3 to 5. The next interval goes from 5 to 7. And the last goes from 7 to 9. At this point, we have at no point introduced the idea of using a left endpoint method or a right endpoint method. The choice of intervals is independent of whatever method we're doing. Okay? That's why, in fact, that I'm not using what's here to denote my intervals. I'm not using what symbol. I'm not using parentheses, I'm using brackets. Okay? So then, when you do this procedure, what you do is you pick one value from each interval. You can be completely random in how you pick a value from each interval, but it's nice if you do it methodically. Okay? In the last problem, what did we do? We picked these values. We picked 1, 3, 5, and 7 to evaluate in the function. Which values did we pick? We picked the left endpoint for each of those intervals. In this problem, we're going to pick what? The right values, 3, 5, 7, and 9, using the right endpoints of the intervals. Okay? This abstract way of doing this problem is really helpful when you have graphs that you can't really work with. You have extremely complex functions, you can still do this procedure. Okay, so now we're ready to approximate the area underneath the curve. So the area underneath the curve can be approximated using the right endpoint method with 4 rectangles. Okay, really it's just 4 intervals. Okay, and we say that we're going to take, here again I'm going to do this a little abstractly, I'm going to do f of x1 delta x plus f of x2 delta x plus dot dot dot, well, it's kind of silly to do dot 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 at that point. I'll step back a little bit. Plus dot 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 plus f of x4 delta x. Okay, what does the dot 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 mean?
So on and so forth.
Yes and no. I like the dot 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 to mean that you should have been able to pick up on the pattern that's going to be going forward. Okay? So for instance, you would never write 1, 27, or 2/7, -3, dot dot dot, right? That nobody knows what's going on. It does continue, but how? So the dot 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 tells the reader you should be able to pick up on what the pattern should be. Okay? Okay, but this, let's be more precise. This would be f of 3 times 2, because our delta x hasn't changed here, right? Okay. Plus f of 5 times 2 plus f of 7 times 2 plus f of 9 times 2. And when you crunch that, what do you get? You get something like 352. Great. Okay. Yeah, units squared, being a little pedantic, yeah. Okay. So, notice that in the last instance, we had an underestimation of the true area, and in this one we have an overestimation. At that point, I mean, you could say that we know the area of the curve to be somewhere between 192 and 352 units squared, but that's not very good, right? But we've developed the method that we need. Now we just need to refine that method. Yes, what do we want to do next?
Like if we were to map.
We could do that. You could take the average of the two and get a better approximation. That's perfectly fine. But here's another way we can get a better approximation. We were only using 4 rectangles. Okay? Let's increase the number of rectangles. So let's go ahead and again let's go back to the left endpoint method. We're looking at number 6 here. And let's do it with 8 rectangles. Okay? So we're going to go a little faster through this one. Here's the first rectangle. Here's the second rectangle. Third rectangle, etc.
You're doing the left hand then this time.
Am I?
Looks like it, yes.
It does look like it. Okay? And I did say to use the left endpoint method up in the
Did it say it up there?
prompt. Yep, right here.
We'll look at that.
It was hard to read, isn't it?
We'll look at
Alex?
it.
No, I'm just joking. All right. So I'm going to start writing this, and then I'm going to get exhausted. So we're going to say that the area is approximated by L of 8, which is equal to F, what? What is the first value that I plug into this? F of 1. Okay? Folks, if you don't have a picture, you need to sketch one. Okay? Because this is, I'm not going to say this is easy, but it's an exercise in sort of bookkeeping. It's not extremely complex, but it just requires that you be careful. So draw a picture to force yourself to be careful. Times, what's my delta x here?
1.
1. How do you know that?
9 minus 1 over 8.
Yeah, let's use that formula. We said that delta x is equal to b minus a over n. So the rightmost value is still 9. The leftmost value is still 1. But what's changed? The number of rectangles is now 8. And when you simplify this, you get 1, which is our delta x. Okay? Plus f of 2 times 1 plus, and I'm tired, so we'll just do f of, what's my last one? What's it going to be? F of 8 times 1. Be oh so careful jumping like that, though. Okay? That requires you have a good picture. By good picture, I mean you don't have to have an accurate graph. You just need to draw an abstract function, but you should subdivide it.